get you to understand this better. So as I said, around this time, they collected this data. It's about the same time WF was discovered. So it seems rather convenient we just make a horizontal shift and find out what is that shifting factor. Okay? And the claim was that shifting factor is remarkably close to WF shifting factor. That's the key. So as I said, my criticism about this shift is equivalent to asserting that the stress is all viscous Newtonian stress came only recently. So it turns out I was eager merely to show that shift doesn't work, instead of criticizing what's the how wrong that meaning is. And so this is the shift. This is, in fact, chapter 12 of the book. So this is the very same data. And there's some glitches, it seems. That is, it seems Kinloch's book, when they tried to produce the master curve, they simply had a smooth master curve, as if they are, okay, so logic is very simple. You can shift until you have the best master curve there is and get a shift factor and compare with the WF shift factor. And you say, oh, they look close. And then probably that's what happened. Instead, we just use the WF shift to shift this. And that's how poor it looks like. To indicate WF does not dictate, does not produce a master curve. But today, as I said, don't bother. This shift carries the meaning that you recognize this process is all viscous, which is untrue. Yeah.
So I just want to make sure I understand that, which is the master curve should be identical if you have should be definitely all that shift.
Well, let's go back to what I said here. So if you have only purely elastic stretching, it's a crime to shift because there is no viscoelasticity.
Right. I'm not saying we should. I'm saying that
So let's just cut the chase. If you just blindly make a shift, the shift factor you find looks close enough to WF shift factor, okay? Period. Is that good enough? Meaning good enough for me to be happy for 70 years? Why not? We were. Which I just realized a few weeks ago that this is the place to hammer a little harder on. Yes. That was the claim. In fact, so much so that there is a confusion about this TTS, the time temperature superposition, and WF. We call that viscoelasticity. You know what? It's not viscoelasticity, it's viscosity only. Where the temperature dependence of viscoelasticity come from? It's only the viscous part. So I can correct all the literature saying, man, we discovered rubber elastic fracture problem is a problem of viscous process. I know you're laughing because it's not even viscoelastic. In other words, all happens is somehow when I change the temperature, something changes. What changes? The viscosity changes. The relaxation time changes, which, of course, in the case of the spirit of polymer rheology, will cause you to access different degrees of elasticity. Because when you change the temperature, you're changing the relaxation time. And if you are fixing the same rate, then the amount of response will be different. In other words, when you fix how fast you stretch, the response still depends on how fast your entanglement relaxes. Which you can affect by changing temperature, which is how you get this set of response instead of that set of response. So back to the story, that this problem was rarely revisited, this notch-free problem. And in the early days, when we report this notch-free problem, we think it's a fracture mechanical problem because otherwise I don't know how to proceed. And by the way, it's just so much going on here. When you know how fracture mechanics proceed, you realize, oh gosh. So let me try not to go step by step. My brain is rushing right now. It's just so in any case, let's take a step back and acknowledge that this parallel universe, there is a parallel universe to this notch-free case, which is to have a notch. And indeed, classically, or the only way you could very conveniently do a fracture mechanical problem is by either peeling or tearing. So I know the tear, I keep saying it's my paper and doing this. And that's what they did. So they find, again, if you, so by the way, by tearing, right, this way, you basically have a force, and then the thickness of the sample is dividing the force, and this is known as the tear fracture energy or tear strength. You can use any name you want. In fact, be patient. This is also Griffith's energy release rate because it has that dimension. Sorry, the dimension of energy release rate is energy per unit area, which is this. Because you multiply a length scale up and down, you find upstairs energy, but downstairs give you area now, right? So, and we are doing all this by really, it's a gigantic step, and we did this by. I have to try to move this thing down a little bit. Oh gosh. So let me try to recap. Basically, we have the parallel universe where through peeling we find the crack speed, which is the peeling speed, which is translating to the rate that you're doing, is such that, again, when I tear faster, it needs more force. When I tear it at a lower temperature, it needs more force divided by thickness. Therefore, it's the so-called tear strength, or the so-called Griffith's energy release rate. Exactly the same thing, that your material is stronger at a lower temperature. Yeah, this is stronger. And your material is, what do I do it? Stronger as you use higher. Let's use a different color. And the material is stronger as you use a different, as you tear faster. So your material is also stronger on shorter time scales. So the rate, the time scale, they are all the same thing, and they all have, when I say it's parallel universe, because this look, how close can you get better? It's just look at this set of data, except totally different things, right? But the physics, of course, is the same, right? In fact, previously, it's recognized to be the same thing. Except there comes the trap. There comes the biggest trap that I have yet to describe to you. But before we do the trap, when you have this set of data, you do horizontal shift, right? Just like before. The bottom is rate. There is a tiny difference, very tiny but very essential. Here, oh God, I keep apologizing, saying that we didn't do enough rheology. Here, this is the rate. This rate could be Hanke rate, V over L, or could be so-called nominal rate, which is dL dt, which is commonly, I believe what he used was this rate, but doesn't matter. Basically, you have rate, which by its definition, it has the unit of reciprocal time. When it comes to here, it's a tear speed. It's a velocity. To relate the two, or if you like, the velocity is not rate. There is a missing length you need to put in, right? Because velocity is some kind of length over time, right? So velocity is not reciprocal rate per se, because there's a length scale. Okay? To cut the story short, very short, we figure, meaning, in fact, it happened at Akron. Our famous Alan Gent professor, who passed away 13 years ago. I missed him so much, I'm sorry. But he suggested that missing scale in one of the very famous papers is 1 angstrom. And he came to my office and says, Shiqing, I'm puzzled by this. This is about some 20 years ago, something like that. I'm puzzled by this. This 1 angstrom is too small. Enough. I'm just trying to give you a flavor of the history. So in any case, regardless of the fact you need a length scale to to relate them, but you can do a horizontal shift, and then you can use the shift factor and compare with the WF shift factor. And I don't know if I bother to, so basically I don't know. I'm kind of running out of time, so I don't know if I have it here. Basically, you can make a shift. Yeah, here is the shift. Do the same thing. You just use WF and shift it. You don't shift very well. So at that time, I have so little else to go by and just say, oh, that probably doesn't work. Okay. So come back to the dramatic part of it, right? So you may as well realize that acknowledging this shift also means, so in fact, amusingly, the shift means you have viscosity and you have velocity. Because this, I know this is R. R, let me use my notation, would be velocity, right? And doing a shift means you put a WF shift factor there and construct a master curve, which, by the way of knowing what AT is just viscosity. So what is this quantity? Actually, amusingly, this has the dimension of toughness. That's just amusing, I guess, for your amusement. For your amusement, but this will speak about this toughness being, again, entirely viscous, right? What else is there? There's nothing else there. So same problem. Now it comes to a completely outrageously lucky situation we have. So let me try to summarize this part very carefully. Remember, I hammered into your mind, I hope, a biggest problem by summarizing the previous lecture, that GC is much larger than gamma. Yeah, remember that? I insist this caused a great deal of confusion. I will, of course, explain this confusion for you in detail now. But first of all, let me use that logic here in a more linear way. Let's put. So, how does this mean? Textbook, right? Remember, I signed you the final. It just asks you to confirm that what I said is not a lie. It's not fake news or anything. I hate to use that word because that implies something very nasty. So I take that back. I really don't like that way of communicating. Because in science, probably we have different convictions, but we shouldn't have any fake news. Okay, that's I'm serious. We may have different understandings. So look at what happens. It's in textbook. It's in Kinlock's book, where what did I do? Yeah, where I kind of insisted that I have trouble with much of what he has in the book when I was learning it at the time. So in any case, how we proceed? Well, we proceed that that this G must be made of a huge part that's dissipated. Yeah? Coming from energy point of view, because that's all you need for energy. So this G0 is really the gamma kind of thing. Sadly, you find even that G0 is much greater than gamma. So we're just completely confused. But let me just proceed to tell you that this is the notion. Not just the book on polymers. Remember, this is chapter 3. He was just reviewing fraction mechanics in general, nothing to do with polymer. So other books on fraction mechanics say the same thing, that there is energy dissipation in this toughness. Largely, I think, because of toughness being much larger than gamma, being the reason. So the rest, I in fact, hope you take time and enjoy reading the rest of it. These are few key statements. So let me come back to how lucky we are. Apparently, the pioneers of fractal mechanics had very little trouble making this suggestion. So let me speculate. They are dealing with steel or metal, and I further confirm most of the time they're dealing with that somewhat above BDT. So if you look at your stress strain curve, it has, metal, so it doesn't yield it doesn't draw like, the beauty of our polymer is it can draw like crazy because of this network uncrossability can, if it's not broken, can allow you to have high strain tolerance. But even if you have this, that would be yielding. And there's enough evidence. If this is the case, there is plasticity. Did I not mention about? I would have to go back to verify. Did we talk about plasticity, a plastic zone? Did we talk about plastic zone? I'm just trying to find out where. It was in last lecture. Here, yeah. So people dealing with the metal were also quite happy. Why not? The way to remedy the problem of stress divergence is to introduce a cutoff of yield stress. And here you are, we call that plastic zone. And I rejected upon learning it because I thought for our polymer well below BDT, there's really no way of having plasticity. Yet your material is brittle. You need to have the same framework to treat the problem. So I was quite unhappy at many levels when receiving this information. But as I told you, we're lucky exactly because of this. So people playing with metals had no trouble of accepting a plastic zone, had no trouble of accepting much of your energy release could be dissipated, meaning plastic deformation process is ongoing even before fracture. Because you can imagine the moment just before GC. This equation would already hold, right? Imagine it's 5% before GC, what do you have? It's still the same thing, no? Yes? I'm trying to bring in a subtle point in some sense. So if you don't get it, it's okay. So basically, I'm saying that we are quite happy that there is a lot of dissipation, which could be either plasticity or viscous flow. Don't ask me which, right? So if you're dealing with a viscoelastic solid, you tend to speak about plasticity. If you're dealing with a viscoelastic liquid, you tend to speak about viscous process. Yeah? So this distinction, I'm making it now for you, right? So in our case, meaning plastics versus rubber, for example. So upon learning all this, we got the luck. The luck is, look at my dear polymeric materials. In either the brittle polystyrene well below BDT or elastomers that elastically stretch under this condition, I should not perceive any energy dissipation. You get it? My polymer material teaches me none of this exists under the condition I examined. For example, brittle plastics well below BDT. For example, elastomers well above TG. So that there is no even confusion of viscoelasticity coming from entanglement, because entanglement is too fast to be picked up. So what else can I say? We just had working in the polymer field become uniquely advantageous, because we can distrust this explanation. Well, not a too strong word. I mean, we can just say, man, I wish I can explain it differently. Right? So I hope we don't have fracture. So I hope I still have your attention. So this is, do we get it? That it's the polymer that gives you the confidence something is fishy. None other than polymers. Something is fishy. Then how you go about it? Right? I think even last time I start to, instead of having you lose sleep, I start to show you how to answer it, right? Did I not? I still vividly recall how I tried to convince you what happened. I'm trying to find that word for you. Oh Lord, I don't find it here. What happens is, oops, God, is this process may not be monolayer. Okay? In other words, this part is monolayer. The surface tension is monolayer in nature. But this whole fracture, which Griffiths precisely and accurately captured, that the so-called energy release rate, remember, is the wrong word. It's really, the rate is per unit area, not time. He was using this, right? Remember, I got, this is called energy release rate. It's written in this form. It's really kind of energy release you can get per unit area. This release does not have to just involve one monolayer. But the Griffiths approach cannot tell. I hear plenty, correctly, of praise about Griffiths' approach. It have all the nasty things hidden and not looked at. In other words, it doesn't go into the tip and find out what happens there. Now, this is, of course, non-controversial. Everyone knows. And in fact, everyone knows today the whole business is about looking at the tip. Well, not today, actually for a long while. But in any case, the Griffiths approach is not straightforward for you to say, oh, this thing simply involves an extensive region, spatial region, which is what I said last lecture. I'm trying to connect dots with you now, by offering you the so-called Krieger-Paris solution, by showing you that according to that result, the stress buildup to a level comparable to the tip stress over a region that is determined by the sharpness of the tip. And the sharpness of the tip, of course, does not have to be a monolayer. In fact, the sharpness of the tip is all the physics, is where all the physics is. In fact, I remember I saying it. It's the mystery of fracture mechanics, is how sharp the tip is. So, in fact, remember the exercise I even told you for window glasses, it will be as sharp as a nanometer. But our polymers is a different game in the sense this sharpness can be very large. So I think I don't want to lose this track, and I want to finish it here by saying two things. Right? I already told you. So we know there's no plasticity for polymers. Plasticity, oh God. That's for plastics. And for elastomers, no viscous flow well above Pg for elastomers, right? So this two things allows us to see things differently. This is for plastics. That's for elastomers. I further give you the mental idea that how do we know it? That's a separate question. That the GC may be very large, releasing a lot of energy because there's a lot of energy stored over a space much larger than a monolayer. But fundamentally, let me criticize now, right? I was always misunderstood by people working in fracture mechanics, as if I was criticizing the concept of toughness of Griffiths. No, that concept, of course, is correct. We use it to rank materials. But it also says that I should look for energy release per unit area, which is what defines this quantity. And conveniently, conveniently or not, I know here I'm coming back to elastomer again. So the story of elastomer is it's really a challenge, because this Griffiths idea is all worked out under the consideration that GC is constant. All of a sudden, I just showed you the trouble of rubber. It's not constant at all. It changes with rate. So now we are forcing this rigid framework. I call it rigid. Forgive me for that. We force this framework to explain the fact that this depends on rate. How do we do it? Obviously, very conveniently, because remember, by now, there is this WF shift, right? That suggests everything is viscoelastic, quote unquote. Or we call it viscous, right? Because it suggests so. But therefore, how convenient this is. The higher rate just have higher dissipation. No wonder. So it's throughout the literature, we speak about dissipation, energy dissipation for elastomers. We speak about viscoelasticity, or the funny word, they call it viscoelastic dissipation. How about that? So I'm suggesting that this energy approach is really difficult. It doesn't directly enable us to look at over what region this energy could be released, and it could not quite deal with the fact this toughness could be a strong function of time, such rate, and by the way, temperature, right? So how temperature comes in? Well, at the lower temperature, you should have more dissipation because viscosity is higher. So it's all fall together. Everything seems to make sense. Everything is viscoelasticity. We can go home and be done. Seriously. And look how we make an effort to do that. It turns out, if I may, because of this behavior that I showed you the actual data on it, we tend to write this as G0, 1 plus F. That's just a form, so that depends on the velocity, or depend on, for that matter, shifting of the velocity, the WF. So that should remind you of the equation 3.5. It's G0 plus another factor that's dissipative and rate dependent. Recognizing that the second term is dissipative. Or, for that matter, you should know that basically the meaning of G0 is the zero rate limit. Sorry, did I say 1? Sorry, I apologize. It's 0, meaning the second term negligible. So let's just entertain and enjoy this logic a little more, right? So how do I get G0 then? Stretch very slowly, for example. Or, since this is all matter of you know too well, or stretch at high temperature. That's the same as stretching slowly. I know this rheological concept or Maxwell level thing is something you should be absolutely always remember. Or look at what this says. See? No, it says so. To get G0 is to do it slowly, to go to high temperature. Or better yet, I can speed up everything by introducing solvent into my elastomers. Because that tends to make everything less viscous, so that I can approach G0. So I laid it full out in front of you our current way of tackling this problem is. And lastly, I will share with you, flipping back to the notch-free case, a statement which is what I should say, the parallel universe. Look at what he said. So he's saying the notch-free case, the variation of this tensile strength and strain at the rupture with temperature and rate, like that of energy release rate, primarily comes from change of monomer mobility, meaning viscous effect that changes with temperature. Okay, so this parallel universe is merged by them. And of course, the physics is the same. It's just the physics being either this rupture or, sorry, be careful, a notch-free sample we call rupture. Either this rupture or fracture, indeed, they involve the same physics of chain breaking. And that chain breaking indeed have the same temperature dependence. And it indeed is a clock on which you measure the time scales on which you are stretching and breaking. So I know I run out of time. What we will do next, I don't think I can avoid doing it. All this is so much of verbalization. So there is a key piece of effort, let's call it, a seminal effort of trying to compute for what G0 is. So I will share with you that model. And since you have done all the other considerations, glassy state and all that, you'll find it's really a piece of cake to evaluate that. And that model says, it was an effort, says I can theoretically calculate and show, in fact, that effort was to do the following, that experimentally, this GC is still found to be much greater than gamma. Sorry, G0. Even this G0 is still much greater than gamma. And so it's not a mono. So remember, gamma is one monolayer. So this model was trying, I hate to say it, stop. This gamma from surface, from some modeling, you can see it should be 1 joules per meter squared. And this Lake Thomas model that I will show you next time actually is also a monolayer, except it tried to make a little correction by saying that if this chain is to break, what released is not just the dissociation energy of that bond, but rather all the other bonds that didn't break also had energy in it. So that was the concept they had. And this is a widely used model, so I plan to briefly mention it next time. And then we go to the experimental part of it, showing whether we should worry about defects or flaws or not through experiment. So that will be the main focus next time. Okay, so I will stop here.